Hey everyone, welcome to a brand new explainer. I am absolutely thrilled to have you here today because we're about to unpack something that is quite frankly a massive breakthrough in Earth sciences. We are talking about a true paradigm shift in how we understand and track one of the planet's most formidable natural forces. For decades, our ability to monitor these events has been anchored entirely in the ocean itself. But today we're pulling our perspective all the way back to the stars. Okay, let's dive right into this. To really understand why this breakthrough is such a huge deal, we gotta start with the inciting incident. Because a magnitude 8.8 earthquake is never just a statistic. On July 29, 2025, a massive 8.8 magnitude quake violently shook the Kamchatka Peninsula in Russia. And this wasn't just some minor tremor. This was a colossal release of seismic energy that immediately triggered a tsunami, sending shockwaves propagating all the way across the Pacific Ocean. Now, when an event of that sheer scale hits, the race against the clock immediately begins, which brings us to the core mystery we are unraveling today. How exactly do you observe a tsunami from space? Historically, tracking a tidal wave meant relying on equipment sitting on the ocean floor. Shifting our focus from the deep sea to a satellite orbiting the Earth, it kind of sounds like science fiction, but as you'll see, it's not just possible, it's an absolute game changer. All right, here's our roadmap for today. First, we'll look at the Kamchatka earthquake timeline. Second, the limits of current tech. Third, the SWOT satellite breakthrough. Fourth, decoding dispersive waves. And finally, the future of forecasting.
Section 1. The Kamchatka Earthquake.
Timing is literally everything when you're dealing with seismic events, and the speed at which this particular story played out is just incredible. At 0 minutes, boom, the 8.8 magnitude earthquake strikes Kamchatka. The ocean floor shifts, displacing a staggering amount of water. Fast forward just about 60 minutes, and a complex, fully formed tsunami wave field is actively radiating outward. And then, at exactly 70 minutes post-quake, something unprecedented happens. The SWOT satellite, moving along its orbit, makes a highly opportune pass right over the region and captures the data. We essentially caught a tsunami on camera from space, right in its infancy. Section 2. Limits of current technology. To truly appreciate that 70-minute interception, we have to look at the critical flaws in our traditional tracking methods. Up until this event, our primary surveillance relied heavily on something called DART buoys. Now, these are instruments anchored way out in the ocean that measure changes in pressure at the very bottom of the sea. And don't get me wrong, they're incredibly useful for triggering initial alerts, for sure. But here's the catch. It's kind of like looking at the ocean through a keyhole. They only provide point-specific data. Imagine trying to understand the full shape and complex movement of a giant wave just by feeling it hit a single tiny post in the water. You completely miss the big picture. When we compare the two approaches side by side, the paradigm shift is just obvious. On the left, our traditional DART buoys give us point data. They measure ocean floor pressure, and as a result, they totally miss the broader wave structure. But on the right, the SWOT satellite doesn't just look at a single point. It gives us a complete two-dimensional view of the ocean's surface. It measures the water level with literal centimeter-level accuracy, and crucially, it detects complex wave patterns that buoys just completely miss. It is the difference between feeling a drop of rain on your arm and seeing the entire storm system on a radar screen.
Section 3. The SWOT Satellite Breakthrough.
Now, what's really interesting about this is the actual visual data SWOT beamed back to us. You're looking at the tsunami wave field near Kamchatka, captured as a two-dimensional surface map. Notice those striking red and blue measurement bands? Well, those aren't just pretty colors. They actually represent the initial sea surface elevation, which allows researchers to simulate and reproduce the surrounding wave field in high definition. We are literally seeing the physical footprint of the tsunami in a way human beings have never been able to see before. And I really want to pause on this number right here, 70. All of those unprecedented details, that incredible red and blue map of surface elevation with centimeter accuracy, that was all captured a mere 70 minutes after the earthquake struck. This wasn't some historical reconstruction done months later in a lab. This was captured live as the danger was actively unfolding. Section 4. Decoding dispersive waves. Having the data is really only half the battle. The other half is actually understanding it. And that brings us to dispersive waves. These are complex wave structures that, remarkably, are often just completely ignored by traditional long-wave models. For a long time, standard models were they were too simple to account for them. But with SWOT's high-resolution data, these waves became impossible to ignore. So it really makes you wonder, if our old models have been completely blinded to these dispersive waves, what critical information have we been missing out on all this time? So the turning point here is that to make sense of this incredibly detailed 2D data, researchers basically had to upgrade their math. They completely abandoned the classical models. Instead, the research team adopted an advanced approach known as a Boussinesq-type model. This specific model was absolutely essential because it could faithfully reproduce the SWOT observations and, finally, accurately integrate the behavior of those tricky dispersive waves into our overall understanding. And this brilliantly illustrates the payoff of upgrading our models. By combining the SWOT satellite's 2D data with the Boussinesq model, researchers achieved an exactitude we have never seen before. They were actually able to pinpoint the exact origin of the tsunami to under 10 kilometers from the ocean trench. That's insane accuracy. The dispersive waves we used to just brush off, they actually acted as a high-definition fingerprint, revealing critical details about the precise seismic source that birthed the wave. Section 5. The future of forecasting. So what does this massive leap forward mean for us on the ground? It basically opens up an entirely new frontier for keeping coastal populations safe. We're now looking at highly accurate tsunami models that finally reflect the ocean's true complexity. We're talking about vastly improved predictions for wave heights and much, much better timing forecasts, so we know exactly when a wave is going to make landfall. And honestly, the best part is that we don't even have to throw away the old dart buoys. By combining this new centimeter-accurate satellite data with our existing sea-based alert systems, we're creating a hybrid safety net that is stronger than ever. We have completely transformed how we see our oceans. We're no longer just peeking through a keyhole at the bottom of the sea. We are watching the whole stage from orbit. By decoding the dispersive waves that our old models ignored, we've unlocked a level of exactitude that honestly seemed impossible just a few years ago, which leaves us with one incredibly powerful thought to walk away with. With the boundless view from space finally working together with our sensors deep in the sea, how many more lives could future forecasting save? Thank you so much for learning with me today, and I'll catch you on the next explainer.